Thank you. First, thank you, organizer, for giving the opportunity to speak today. And Singularities, we are diverse with mathematicians in different areas. We're going to start with a brief introduction to Singularities. Okay, so let me start with a little motivation. So we're going to take polynomials over the complex numbers, and we're going to take its vanishing set now at the points that are related in that polynomial. We're going to say that f has a singular point b naught if it vanishes, if f vanishes at 0. And all the partial derivative of the polynomial vanishes to that point. So if this happens, we'd say that f has a singular point. Otherwise, we're going to say that b naught is a smooth point in B. And since I come from algebra, I know that sometimes I would want to say that something is regular instead of smooth. They are not always numbers, but in a lot of cases. So if I say irregular, I mean smooth. So let's see some examples. So here it looks smooth. So what the definition tells us, arise a little bit. And here we have a singular point, and then here we see that the 0, the origin, is the only singular point in this variety, in this vanishing set. And we can also see it from just looking at the timing space. Here, the timing space is well defined everywhere, but here at the origin, we have the options, and variation is not seen. Okay, so we have other samples. Now we have surfaces. One that's smooth, one is singular. These images were taken from imaginary, and they were done by Hauser. So let me establish a little bit of notation. For us, K will always be an algebraic cross field. It's not always yet. It's unless then this. S is always going to be a polynomial thing over K with 3 variables. I is always going to be an identity S, and R is going to be a quotient between S over I. But another way to say it is R is always going to be a finite integer. Yeah. Okay. So let's try to do this singularity theory a bit more algebraic. So then, if I want to take the vanishing set of, I'm not going to take only one polynomial, I'm going to take a bunch of polynomials. We're going to look at the vanishing set, other points, in which every single polynomial in the ideal vanishes, everything becomes zero. And when we do this, we have an algebraic side. And this is given by the spectrum of R in R. And this is filled with second topology, sense topology. Here we have the geometric side. Here we have the algebraic side. So we have examples again. So if we look at the vanishing set of the spectrum given by this equation, here we have this kind of number. Here we get the cos of it. And then how we find the equation? And then we have it because arises are telling us that this should be somebody spurious is just going to be the full dimension. We have also surfaces again from imaginary. So here we have polynomial in 3 variables over this. That's called the polynomial. And then here we have the derivation. So this we have again. We're just looking at the correspondence between the geometry, the nice pictures, and the algebra. Here we have another. This is the bat. I took this picture from Meltonster's website, and we can see here that the bat has a singularity at 0 because 0 vanishes, but also 0 vanishes in each of these derivatives, which is going to be 2x squared, and then the other derivative is 3y squared, and then the other derivative is minus 3x cubed. Okay. So We have a dictionary between algebra and geometry. So when I look at points here in a vanishing set, this corresponds to taking maximal ideas in the ring. So ideas that are not contained another idea that is different than R. And the correspondence is given by, you give me a point, I'm gonna give you this idea which just corresponds to all the polynomials that vanish at that point. So that point has, for instance, entries A1 to A3. So this maximal idea is generated by x1 minus a1, with xt minus a3. So we have this nice correspondence. So we want to see the similarity. Sometimes we need to go the functions that are defined to certain points. So here, when I take R and then I write this little n with b, what I mean is taking R rational functions. So f over g, but I want this to be defined as a point. So g cannot be 0. So I will request that g of b is different than 0. And this is process localization, because we're somehow looking at the rational functions that can be defined like around that point. This is can be done because g of b is different than 0. But if we want to do it not only for points and for maximum ideas, we want to do it for a prime. Well, we have to modify this a little bit, and what we're going to take is R at Q, or localize at Q, is going to be all the rational functions, and instead of asking that something doesn't vanish, is going to be for the analog to ask that this element is outside Q. And this is the way we can look at functions that are somehow defined around this point. It's prime element. And this has the beauty that this has only one maximal identity, which is going to be the extension. Okay? So there are different tools to the singularities. In the beginning, we described the definition was given to partial derivatives for an idea that is defined by different polynomials. We can do it with the equivalent rematches, use anti-vector calculus. And if you are specializing in algebraic geometry, another function that's very important here is the degree, but since I am an algebraist, I like to that in person. But there are different tools. Well, now we're going to move to prime characteristics to discuss different kind of fluids, and the main one is going to be the Frobenius map. That map that sends us an element to the P power, assuming that P is a prime number, which is a characteristic of the field. So this map, the Frobenius map, we're going to denote its image as R to the P. Every element is the power of something. And what we're going to have is, because this is an image, this is contained in the real. But this is also a ring. So what's going to happen is R is going to be a model over RP. And this is going to tell us a lot about what's happening in the ring. So let me just iterate from this map. So to do this repeatedly, so R is sent to R to the P to the A. And again, we have the R is an R to the P to the A model. And then we have a series of rings. So we have R, we have RP, RP squared, and so on. And if R is reduced, for instance, if R is a ring, what we're going to have is that this as a ring is isomorphic to this one. The map from here to here is Frobenius, because we know that's the image, so the map has to be subjective. And because the ring is reduced, it has no need, so this has to be injected. So this as a ring is isomorphic to the other. But this one is smaller. And then we doing that over and over. And to me, and this my intuition tells me here there is a prime. Because we have a smaller ring, which is isomorphic, that's self-similarity. And this kind of intuition has been used to obtain the fractals that we are used to. There are different results in the value P that do rely to things fractals that are more what we're used to. These I took these two pictures from a paper by Nunez-Betancourt. Okay, what we are some here are similarities. But let's use this probability map to detect similarities. So we say that a ring, sorry, we have that the ring R is regular at Q if and only if, well, R is a module over R P. So it's going to be regular or smooth if this guy is free as an R P module. So the freeness of this one over as free is telling us whether the ring is regular or smooth or not. And if we are able to do it just with the image with RP, it's going to be equivalent if we do it for P to the E. And here it will be for every E is bigger than 0, for some E bigger than 0, or for this E equal. And all of this is so we have a tool that only sees prime characteristic to detect singularities. And we want to do is use this tool not only to detect singularities, but also to measure to see if something is not regular, then this is not going to be free. And we're going to use this point to see well if something is far from being free, it's probably far from being regular. For this, that we're going to start working on. We need to take the generator. So here is the same as before. I just add the generators. And these generators, well, they are going to belong here. The number L depends on E. Depends on E. Yeah, and because this is free, what's going to happen is just the rank of it. That's what I mean. Which is going to be P to the data dimension and whether there is some. The ground field is when this case is and the right okay. So let's just set P to be the characteristic of K. So we say that the ring is pure if RQ may not be free, if it is not regular, it's not possible. But at least has one free part. So it has a free part and something else. May or may not be free, usually it's not free. It's not regular, but we say that it's pure if at least has one piece that is free. And this is for those who work in rational geometry in characteristic 0. This relates, for instance, with something being low canonical, even though it doesn't relate there is a connection. That is one. Okay. Let me give you examples of things that are pure to show that this happens often. So the first one is if we take, let's suppose that R is a polynomial ring and I is an idea generated by square free monomial ideas. Sorry, here it should be S, I'm sorry. So if we take the question, this is what's called a standard ring, which is one of the main connections between combinatorics and multivariate. So these rings are pure. If we have a group actions nicely, in a polynomial ring, then the difference of invariance is pure. Very nicely, according to the training, is you have a range of separation back. The rings of invariance are also pure. And you take a matrix of variables and then take I, the idea generated by its L by L minus, then the quotient is also pure. I want to point out that in prime characteristic, the third example is doesn't come from the second. Because in prime characteristic, we will have that this ring of the variance are always, but the dominant rings are not always in the exponent, we don't always have the radius for time. And another that it is included in the second one, but I want to point it out is normative variance. You take a final normative variance. You take a semigroup ring where the semigroup is normal, then it is pure. And another, you want to do this one of an electric curve. And this is gonna be a cube if P, the characteristic is congruent with one modulo of P. But if P is congruent with less one modulo of P, then it's not a cube. So there is only some argument over that. Okay, so let me use this problem to define something that is going to measure singularities. So suppose that R is pure. So the pure threshold of R is defined by, and then we make sense of it because it looks a little bit technical. So what we had before is if the ring is pure, then it's going to have a free part. Something else. So we look at the generator of this free part. And what we're going to check is what is its order. So what we do is take that order, which is always bounded by E. It's always smaller than E. We look at that, or sorry, by P to the E. We take the ratio, and then we take the limit. And it turns out that that didn't exist. And that's going to be called the pure threshold of R cube. So if you were wondering what is the order, what the order is, well, I just look to that element. And I'm going to see what is the maximum power in which F is at Q to the okay? So this is going to be the pure threshold. And these have nice properties. For instance, it is a rational number in many cases. So, Nunez strings, determinant rings. But at the example that I mentioned before, in all of those cases, this number is a rational. Sorry, it's a rational number, and is to the best of my knowledge, there is no example of a ring where it has found that it is rational. So this number is going to be bounded below by 0 and above by the dimension. And this number is going to be equal here to the dimension, even when we give it regular at Q. So what's happening is this number detects singularities. And the philosophy behind this is the closer this is to the dimension, the better the singularity is. For those who are familiar with numerical algebra, we're going to see that this number is also about for the depth. So the closer this number is to, the bigger this number is, the bigger the depth, and the closer is going to be open according. If somebody works with numerical algebra with more than 7 resolutions, well, this number also tells us about that as a long regularity, which is how these matrices that appear when one is generated. So this number tells us how the pure threshold gives us a pattern for the matrices, the release of the matrices that appear there. So it appears in different aspects of algebra. But it has a problem. So for the case that we mentioned before, well, the number is defined for local rings, or when we localize we're looking exactly what happens in a point. And this, well, if we look at this one, the maximum homogeneous area, that the threshold is going to be 0. If we look at any prime that is not 0 and is not the maximum, then it's going to be 1. And then when we look what happens at the smallest prime idea, which is 0, then it becomes equal to 0. So this number does not behave well when we want to see across different points what's happening across moving. Sometimes it's going to go up, sometimes it goes down, and that's a bit problematic if we want to study the pure threshold as a function from the spectrum of the ring to the real numbers. And we want to correct that. That was the motivation for this work. And for that, in the young work with Alessandro De Stefani and Ilya Smirnov, we defined the effect of the pure threshold at Q as the difference between the dimension minus the pure threshold. And this is a minor variation. It's just like we put a negative sign and then add some. But this is enough. This is enough to have good behavior in many cases, and we will see it soon. So first, this number, well, the next one is properties that we have the compressor because it's just like a very mild modification. For instance, this is going to be rational in other cases that the compressor was. So, second, this is also going to be between 0 and the dimension. Because this is going to be equal to 0 if the compressor is equal to the dimension, and this is going to be equal to the dimension if the compressor is equal to 0. Not surprising yet. And the effect of the compressor, well, again, it's going to be 0 if only if the ring is regular. And the effect of the compressor is going to be bigger or equal to the dimension minus the depth, again, from before. And this is sometimes called the invariant. And the effect of the compressor is going to be bigger or equal to the Casanova regularity when it's working with great regulars. And again, here now the philosophy is the smaller the fact that the is, the value is the singularity, because it's working being regular. Okay, so one property that this does satisfy, that the equation does satisfy, is if we go to a smaller price, we get a smaller number, and smaller the and that is because when one goes on the smaller prime, one expects that the singularity is going to improve. So the number should be closer to 0, because 0 is the best. For the 0 is the best to have, not because then everything is regular or we have smoothness. And we can see it in the example that we had before. So at the maximal area, well, that has dimension 2, and the curvature was 0, so the DFPT is 2. And here what we know is that this is going to be regular, so the DFPT has to be 0, and the same when we don't price at 0. So this number does behave better. And this is it's all the problem that we had before. Because smaller prime is there, smaller invariant. But it has other properties. So for instance, if you were working on a theory, then when I look at the map, which was the initial motivation, looking at the map from the spectrum to the real numbers, defined by sending a prime middle cube to the DFT, the effect of the threshold of that ring at that point. And it turns out that this function is over semi-continuous, which is very nice. So very in a regular value, right? This is a property that one wants to have when we're studying these kind of things. And if somebody doesn't remember what over semi-continuous, you haven't taught calculus in a while, let me just tell you that in this context, it means that the set of prime ideas such that the function is, so in this case, the DFT is smaller than A, is going to be open for every equation, for every real number. But we were able to get something slightly stronger, which is the function is not only over semi-continuous, it's strongly semi-continuous. Strongly over semi-continuous. That means that what we had before, instead of having smaller, now we have smaller equal. And one can see that this implies the previous ones. Okay. Okay, now suppose that a ring is a pure and equivariant. I want to avoid defining equivariant. But for instance, let me say, for instance, that every complete intersection is a emitter for equivariance, and there are like several examples. But in this case, if we look at the map that we had before, that sends a cube to this to the fifth vector of this dotted ring, we have that has a finite set of values, which which to prove this, we have to use a various theorems. So we have a fancy values, and you want to look a value, and then the pretty much the primary that we have is one of the nice simplification. Comes with other invariants for those papers I want to listen. Okay, so now well, we have other kind of theorems. This is more geometric. If we take an irreducible projective variety and a lambda, let's bigger become 0. So then, if we have that the effect of the response in every single local name associated to a variety, the DFPT is strictly smaller than lambda. And then we cut that variety by a general vector plane. We're gonna have the DFPT of every point in the cut, in the intersection of our original variety with the general vector plane, is gonna have also smaller than lambda. So if we think of the effect of the progressor as something being the smaller is good. When we set this bound, when we call the general plane, is still at least as good as it was before. This is a working type problem. It's invariant. If we have X is a locally pure schema, and this means that every of those local rings are pure, and then we have the block with respect to a closed point. And we assume that the sectional divisor of pi is arithmetically Gorentz and globally pure. So this is just in technical, let me just skip defining this. What we're going to have is that the DFPT of the block is going to be smaller or equal. The DFPT of the block is going to be smaller or equal than the DFPT of X, which is going to be the same as the DFPT of the sectional divisor. Now, why by the DFPT of a variety? Well, just the maximum among all the terms around. And this is telling us that when we get the block, it doesn't become worse. We would like to become better. And that's something we have been trying to work, but we haven't been able to prove. Because so what is highlighted? Well, the goal of the thing here is if we were able to prove to take this line away and say that this is simply smaller, and then somehow we can interpret the problem. So we will be having like a method of looking for the solution of singularities. But we don't have that. Sorry, right? Oh, no, that's improvement. That's part of the problem. Yeah, no, it's not. And and what I say about the dream, I mean, there is a lot of issues here that one has to be able to repeat, like get a limited regards. So there is a lot of problem. Okay. So let me just mention a little bit more of applications of these to what's called free singularities. So for this, I need another definition. So we say that the domain R is strongly regular for every element in the ring different than 0. Here, different than 0. We have decomposition where R has that free part, but that free part is generated by R. So we have for some E bigger than 0. So another way to say it is this element generates some free particles and actually playing mode as long as E is big enough. So this is the definition of strongly regular. For those who work in rational geometry, this is somehow the analog of this connected to get singularities. Okay, so we say that polynomial f is square free if every monomial in its form is square free. So you have a bunch of square free polynomials and you take a linear combination. Thus, For instance, the determinantal and the negative matrix, actually definition, but taking the linear combination with ones and minus ones of square free polynomials. And there is this paper by Daniel Bat and Louis Walter, where they take matrix and with this they build a polynomial that's a linear combination of monomials that are square free, and these monomials are the base series of the matrix. And this turned out to be a square free, and they do this because, well, there are relations between the matrix and the polynomial. There is a paper. So these are square free polynomials. And one thing that we were able to prove recently is that if f is an irreducible square free polynomial, then our equation S over f is strongly regular. So it has nice similarities from the point of view of characteristic 0. And this result doesn't have any FPT, but some of the things that we did define. So the FPT are related to this one, and we need some other stuff, and this is where Aldo Conca came into the picture for this chart. And now that we did this, we were able to compute the FPT of this square free polynomial, and it turns out that is going to be the same as the universal multiplicity minus 1. And remember that universal multiplicity is equal to 1, and underneath that it is regular. Okay. And as a consequence from this kind of dictionary that has been built in characteristic 0, characteristic P, well, if we are over a field of characteristic 0, and you take a square free polynomial and then take the variety given by that, then that variety is going to have rational singularities. This is a recent paper that was posted in the archive last month by Bad, and Walter. And in fact, in that reprint, they have some question whether the analog characteristic 0 will be a rational, which corresponds to the rational variety. And what happens is only regular things are the fractionals. So the previous theorem solves the open question that they posted. And this is a consequence of that. Because once you have one of these polynomials, square free polynomial, you look at the equations as regular, and the coefficients, you build like some sort of approximation of this characteristic P. And if for infinity P or for P big enough, you have that is a rational, then the original is going to be rational. And so this is a consequence of the previous term. Okay, and then there is another corollary for the square free polynomials. So you take G and H square free homogeneous time. Previous times we didn't need homogeneous, but here we need homogeneous polynomials. Satisfying that the degree of H is exactly 1 bigger than the degree of G. We take almost a linear form. So a linear form, and then we add 1. And then we take F equals G dash L plus H. What this is going to happen is that if G is irreducible and does not divide H, then the quotient is going to be strongly regular. And these these polynomials come from some relations. So if one has diagram, which comes from so number Daniel, Bat, and Walter were studying famous dynamics and integrals. And they relate these diagrams polynomial. And then they were studying the singularities of a polynomial, which is going to look like this one. And if those singularities are rational, then one can say something about those integrals, about the convergence of those integrals. So what we did is we proved that those polynomials are strongly regular, and then as a consequence, we have that they are rational characteristic 0. Okay, so I mentioned now a lot of the results, and I haven't shown any of the differential operators. And I say that the title of the talk was Frobenius and Differential operators measure similarity. And so far, we've only seen Frobenius. So let me mention what is the main thing that we do for all of these. And there is what we are going to see the differential operators. So the set of differential operators at most n are defined in those areas. So the differential operators for the 0 are going to be just the morphin ring of R with itself, which is going to be isomorphic part because every map from R to M is multiplication by n. And everything that is R linear will have to be C linear. And then the differential operators of order almost n are going to be, well, I take all the C linear operators from R to R, and then I'm going to take the commutator of that delta with all the operators of order almost 0. So this doesn't look like it, but this is somehow a way to have some sort of plane in the world. This is it's not a different related. And some properties of these ones is, well, as I was mentioning before, the differential operators of order 0 is just
There you go.
okay. So and then we're going to have that if something has an order almost n, well, it has an order almost n plus 1. And then this property that you multiply something of order almost a with something of order almost b, and then by multiplication of the position, we get something of order almost a plus b. The differential operators for order 1 are going to be all derivatives that are C linear, C linear, plus the D0, which is just the number of frames from R to R. And then something that usually happens is this container is strict. Usually we are going to get here in, for instance, in D2 that doesn't come from the value to this property 1. And this is related to the short of Nakai that says that when characteristic 0 says that there are no differential operators with the derivations, even something like that. So one expects that that conjecture is going to be true, and if that conjecture is true, usually this is going to be stated for all communications that is not seen. Okay, so the ring of differential operators is going to be just the domain of all the differential operators in order, and this is non-conjecture. Okay, so let me just give you an example in prime characteristic. So, because we're working in prime characteristic, these we have to take not only the derivation, but also how divided powers the derivations. Here we are not divided by 3 factor. This is wrong, we're not divided by 0. But this whole symbol is because this operator behaves as if we were to be divided by 0. But in reality, this is just given by some different coefficients that the rest. And in prime characteristic, we have this really nice characterization because every differential operator is going to be arbitrarily linear by some e big enough. So every differential operator here is just It's just related information. And these elements, the differential operators that are to the linear, is what's called the 11 differential operators. And then here we're going to do something that can be characteristic P, and what we're going to do is combine these two iterations. On one side, we have the real differential operators by order, and the other side we have by 11. Here what we're going to do is just put them together. And it's not only because we can, it's because this is going to tell us things about the range. Okay, and then to start giving a better description, let me produce some notation. So if we have an idea, it's bracket p to the powers is just take the image of that idea on the iteration of Frobenius and then extend it in the ring. But what you see it is, well, just take the idea generated by the p to the powers of every element in the idea. And we are going to take polynomial ideas of I with I bracket p to the a, and this is just all the elements in S, the polynomial rings, such that S times I is contained in I bracket p to the a. So it's easy to see that this I bracket p to the a is contained in I. We're going to the elements the same, the bigger one to the smaller one. Okay, so there is famous criterion by Feather to know when an open ring is secure. And this coming test, and you can test it in a pretty two singular. So you have an ideal and you take a maximal ideal. So you take I within S, you take a maximal ideal in S. Well, it's going to turn out that the question is going to be pure at N if and only if the column ideal that we described before is not contained in a bracket p to the a. And the thing is that other elements that are not in n bracket p to the a somehow give us a free path of the question. The problem with this test is that this is local. Tested, we need the maximal ideal and bracket p to the a. If we want it to be pure for everything, we have to test this for every single maximal ideal. So we change this test to a test with differential operators. And so here we don't that maximal ideal, like that. So if we have an ideal S is the same, the polynomial ring, then the whole ring is a pure period, not a sum. This is pure. When we take these differential operators that are ordered t to the p minus 1, comma p, so level 1. And then when we take every single operator here, and we evaluate it in every single element here, and we take the idea generated by those, is different than the ring itself, then the thing is pure. So we go to have some sort of global test for purity, which is going to allow us to test things, see how the things behave when we organize in a different prime ideas. This is what allows us to study the thing, not only at the maximal area or prime area, but like global, like in the what we have with spectrum. And then to relate this to the effect of purity, to test it. So we're going to take this invariant, theta is I, which is just testing it. Maybe you have something to say pure, we know that this works. So we have P, and then this works. But now we're going to do it sort of P to the E, and then we're going to try different ends, maybe not as we go to the top, some. And then we're checking what of those help us to test purity. And it turns out that this number, when we take the limit, so we take that over p to the a, and then we take the limit, that limit exists. And indeed, it's going to be related with what's going to be the maximum the expectation. So here, I mean, there is a lot of definition, there is a lot of terminology. But the whole point is that this number that is only with Frobenius that can be defined in terms of an invariant that depends, the invariant that can be defined with differential operators log. And because we have this connection, then we're able to get other terms about activity, spatial certification, the routine type, all of those. And that's it.